Now we are being asked about the mean and standard deviation for this situation. Now, to find the mean of a binomial distribution, we'll say that the mu is equal to n multiply p. Now, n, of course, is the size of the sample, and p is the probability of success. These are the only two quantities we need. So we'll put labels in column A once again. Our n is still 21, and our p is still 41%. All we need to do is say equals the n multiply p. When we press enter, we'll find a mean of 8.61. For the standard deviation, we have a new equation. The standard deviation, or sigma, is equal to square root of n times p times q. N is still the size of your sample. P is your probability of success. And Q is the probability of failure. Now, the probability of failure is always going to be 1 minus P. Now, since we already have P, let's come down slightly and find out what Q is. And we'll say equals 1 subtract and click on the 41%. We get a probability of failure of 59%. Now, to find the standard deviation, we say equals SQRT for the square root symbol. Click the n, multiply, times p, multiply, times the q we found. We're not going to use the mean here, so we'll skip over that. When we press enter, we'll get a standard deviation of 2.25386. I'll paint those cells gold to show both of them are part of this answer. Now, to find the range of values that are usual, we'll need to do a little more math. Our low value for usual is going to be the mean minus 2 times the standard deviation. To get the highest usual value, we'll take the mean and add 2 times the standard deviation. Since we already have both the mean and the standard deviation entered into their own cells, we can reuse those cells for problem J. We'll say that our low value equals, we click the mean, subtract 2 multiplied by the standard deviation. This gives us a low value of about 4.1. Our high value will be the mean and then add 2 multiplied by the standard deviation. Press enter, and we'll get a high value of about 13.1. So we'll say that our usual values, or not significant values, will be between 4.1 to 13.1. If we make a drawing, we'll place markers at 0 and 21, where the distribution starts and ends. Now, we'll place a marker at 4.1 and a marker at 13.1. And if we drew our bell curve, most of our bell curve would fall in between those two numbers. It might look something like this, where you would have tails extending toward the 0 and toward the 21. If we do this experiment again, we have a 95% probability of ending up somewhere between those two markers. Anything that falls outside of those markers would be considered unusual. Anything inside is considered usual.